Bismillahirrahmanirrahim. Greetings. This is going to be the third video lectures that I'm uploading about the concept of implicit differentiation. Now, as I have mentioned in the first video, there are quite many equations that they are mixtures of x and y. Some of them we can separate x and y so that we can write y as an explicit function of x, so that we can apply the rules of the differentiation. And some of them we cannot. Now in this video we are going to find a way so that those that we cannot separate x and y, so that y cannot be written explicitly as a function of x, can we still use some of the rules of differentiation? Can we still find analytically the rate of change of some points in those curves? Now, one strategy in mathematics, in solving problems in mathematics, is that if the problem is a bit difficult to start with, it's good to make your own kind of examples, or seek for an example which is related to that, and those that so that you can extract information from those examples that you're already familiar, and apply that one as a hint so that you can solve the problem. You can come up with a solution. Now, you can also use this concept for some concept of course of mathematics that they are a little bit abstract. So you can use some kind of example of your own, or seek for an example, so that you can kind of melt away the abstraction and make it more comprehensible and more concrete to yourself. So this is the strategy we are going to use in this lecture to find out about implicit differentiation, and see if we can differentiate those kind of equations that they are mixtures of x and y, and so that we can find the rate of change of the graph of them, that we have no access to the graph of that, and we don't even know how the y is looking in explicit form, but still we can apply some rules of differentiation. So this is going to be the strategy we are using for this lecture. So let's get started, shall we? Okay. I have here, we are familiar with circle. So I started with a simple example, and a circle of radius 3 I selected. So the equation of that, the equation of the circle will be x squared plus y squared minus 9 equal to 0. So this is a mixture of two variables, x and y, and is what is a circle. And the good point of that is that we can separate x and y, so that y can be written as an explicit form of x. But we don't want to do it so that we can extract information. Do you follow me? Okay, now I go ahead and differentiate this side. I don't use the word implicitly because I haven't defined it yet. I haven't talked about it yet. So I'm going to differentiate both sides, assuming that y is replacing, y is substituting some kind of relation that is a function. Based on that kind of assumption, I'm going to start to differentiate this one using chain rule. So derivative of x squared is 2x, derivative of y squared, that y is replacing, this y is replacing some expression in terms of x, by chain rule is 2 times y power 1 less times derivative of y. You follow me? So here I have written. Then I go ahead and solve this one with derivative of y with respect to x. And I end up with, similar to the original, is an equation in mixture of two variables in that case. Now I want to see if this is correct, if this strategy that I'm using is correct or not. So I go ahead and write separate x and y, and write y as an explicit function of x. Because once y is an explicit function of x, then the rules of differentiation can be applied. So I go ahead and do that, y equal to a square root of 9 minus x squared, and then differentiate that one. And we are familiar with how to what the derivative of that will be. The derivative of that will be minus 2x over 2 square root of 9 minus x squared. At this stage of the course, students are familiar with this kind of the differentiation, how to take the derivative of that. Okay, now when I simplify 2 and 2, they cancel each other. I end up with this x over a square root of x 9 minus x squared. But 9 minus x squared is same as y. You see that? Same as y. So if I put this one y instead of that, I get exactly same as I got without knowing what y was in its explicit form. You see that negative x over this is same as negative x over y. They are both same. So I'm kind of excited. Looks like I have got something. I have noticed something. I'm using again a strategy of what problems that I know about, I'm familiar with, to find out about information about the things that I'm not yet familiar with. So this is the strategy. So now let's see what else I can come up with. Now let's see what we notice. What is the motive? We noticed that from the previous page, we noticed that y was a function of x in its explicit form. We noticed that because when we solve for y, we end up to y equal a square root of 9 minus x squared, which is a function of x. So that is one thing we noticed. I wrote it here. Now, we also notice something else, that if, notice about this one is very important, if y in its explicit form, this is the explicit form of y, if we replace that one in this equation, we'll make that equation as an identity. We know what that word identity means from the previous lecture. If you haven't watched it, please, I strongly encourage you to do that. It's a short lecture. Now, if I replace y with this, which is in explicit form of that, will become identically equal 0, which means that is 0. This is another way to say 0, in fact. That is another way we can say 0. For example, for 0 we can say 1 minus 1. For 0 we can say 2 minus 2. So same thing is we can say here. If we replace y with this explicit form. So in this observation that we made, we put this one, we make these two as a properties that y should possess as a prerequisite, am I pronouncing correct? Prerequisite for the for the implicit differentiation of equations in this form. So these two properties that we notice from y, we use these two properties as a requirement, so that we can proceed to go for implicit differentiation. So when an equation is given to us, which is a mixture of x and y, and we cannot separate x and y, so we make two assumptions before we proceed to use implicit differentiation. And the two conditions that we impose, that we accept, based on them, based on those assumptions, we proceed. One of them is what? Y is a function of x. Second one is that if y is replaced in that equation in its explicit form, if it is replaced within its explicit form, will satisfy the equation and make the equation, in fact, an identity and absolute equality. Do you follow me? So these two we impose, and based on those, we start to use implicit differentiation. Are you with me so far? Okay, now let's go to a problem. Let's just together let's solve a problem related to this. Okay. Now this is the problem we are going to go and solve it together. Now, I've repeat in case, they're large enough I have written so that they are readable for you, but I read them so that in case if you could not possibly see them clearly, you can always take notes from my voice. All right? All right. Now, by implicit differentiation, we know that derivative of y with respect to x equal to negative x over y for this equation of circle. We just did that a minute ago. So we know that is the case. Now, question is asking, he says, determine the rate of change of this curve. This is a curve, a mixture of two variables. Determine the rate of change of that curve at 1, 3 at the point. At point 1, 3, so determine the rate of change of that. So what do? You put 1 for x, and you put 3 for y, so become negative 1 over 3. You follow me? And not so fast. Not so fast. You cannot do that. Why? Because 1, 3 is not a point on this curve. It's a point somewhere else. We can't find the slope of a tangent line of a point in the plane. Doesn't make sense. We have to have a curve. This point is not on the curve. How do I know? Plug it in for x1, for y3, you get both, you get 10, and 10 is not equal to 9. So this point is not here, so the reason I selected this example, don't let that this formula to fool you in a sense that you think, okay, I got that one, any point you give to me, now I can find the rate of change analytically. I can find the rate of change of that curve at any point here. That is not at any point. No. But most of the problems that they give us and they want the rate of change for the curve, they do tell us. They say at this particular point, at x1, y1, which means they are giving us based on the assumption that that point is already on the curve. But if they do not, then you have to test it. And if it is satisfy this one, this one satisfy this one may not satisfy the original equation. If it does not satisfy the original equation, the given point, then you say I cannot discuss it. I cannot say what is the slope of a tangent line on the graph of that curve at that given point. Do you follow me? Now, one other thing you have to make observation. Look at that. X squared plus y squared minus 9 is the equation of a circle of radius 3. What is the derivative that we find just a minute ago? Implicitly, we find out the derivative of y with respect to x to be negative x over y. Is that right? But the strange part is that the very same is true for a circle of radius 5. If I differentiate this one, implicitly I get the same, negative x over y. It's getting complicated, huh? Now, the same is true with a circle of radius 10 in this one. So what's going on? If I say what is the rate of change of this circle, let's say at let's say 0, 3. 0, 3 satisfies this one. It is on the curve of that one. When x is 0, y is 3, and that the slope of the tangent line is horizontal at that point. For this, yes, but doesn't satisfy this one. 0, 3 is interior of this circle. It's not on the circle. 0, 3 is interior of this circle also. So it satisfies that one, but does not satisfy this one. So there are kind of a little bit tricks that you have to be, that's what mathematics is all about. Think, contemplate, reflect. Don't become mechanical. Don't just start to do without thinking. So whenever the problem is given to you, try to think, reflect, see what you should be doing, and etc. before you start. Don't be mechanical. Okay, then I thank you for watching, and in the next video I will be solving some related problem, and I hope that these lectures are beneficial to you. Okay, then again, as always, I wish you all prosperity and good health, and please stay safe. So long.